Hello there, and welcome to the Sleepy Space Channel. There is an order to the way an intergalactic crossing kills you, and it is not the order most people would guess. 2.5 million light-years separate us from the Andromeda Galaxy, and along that route sit the expected hazards: cosmic radiation, the slow failure of the ship, the ruin of a body that has lost its weight, and deep time itself. All of them are fatal, and all of them are slower than people assume. None of them is first. What reaches a traveler first is something the plan carries aboard on purpose. Over the next 2 hours, we will work down that order from the back. If you find these explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next 2 hours, none of this is something you need to carry. Nobody is making that crossing tonight. Settle in. Let your shoulders soften. Let your breathing slow. Let the day fade away behind you. Let's begin. Part 1. The gap itself. The Andromeda Galaxy lies about 2.5 million light-years from Earth. It is the nearest large spiral galaxy, the nearest object in the sky that genuinely resembles our own, and one of the very few galaxies whose light arrives blue-shifted rather than red-shifted. Blue-shifted light means approach. Andromeda is moving toward the Milky Way at roughly 110 kilometers per second, and it has been doing so for longer than there have been eyes to notice. That approach is measured from the way its spectral lines are shifted toward the blue end, one of the earliest indications astronomers had that not everything in the sky is moving away from us. Of all the places outside our own galaxy that a traveler could aim for, this one is the closest, the largest, and the only one that is coming to meet us halfway. Written in kilometers, that gap is a little over 23 quintillion. The number is not useful at that size, and the mind does not hold it. What matters is what the number does to a schedule. Distance in space is not an obstacle in the way a mountain range is an obstacle. Nothing about the gap resists a ship or pushes back against it. The gap simply takes time, and it takes so much time that every other problem in the crossing gets the chance to mature. That is the quiet property of this particular hazard. It does not act. It only lengthens everything that does. Andromeda is the largest member of the local group, a gravitationally bound collection of more than 80 galaxies spanning roughly 10 million light-years. Most of those members are small, faint dwarf systems, and the group is dominated by 2 heavyweights, with Andromeda slightly ahead of the Milky Way in mass and stellar count. The third largest member, the Triangulum Galaxy, is a modest spiral that may itself be bound to Andromeda as an oversized satellite. The center of mass of the whole group lies somewhere in the space between the 2 large galaxies, drawn a little toward Andromeda by its greater weight. Everything in the group is falling, slowly, toward that shared center. The arrangement has been stable for billions of years and will remain so. Because the local group is bound, the expansion of space will never separate us from Andromeda. This is worth sitting with because it is the single feature that makes the destination reachable in principle at all. Every other large galaxy in the observable universe is receding, and the more distant ones are receding fast enough that no ship leaving today could ever catch them. Their separation grows faster than any craft could close it, and over deep time they will slide beyond the horizon of what we can even see. Andromeda will not. Gravity holds the local group together against the general spreading of everything else, so this galaxy stays where it is relative to us, and then comes closer. It is the easiest intergalactic destination that exists. The galaxy itself is a substantial place. Andromeda holds something on the order of 1 trillion stars, several times the count of our own galaxy, spread across a disk somewhere between 150 and 200,000 light-years wide. It carries its own retinue of satellite galaxies, several dozen of them, scattered around the main disk in a loose swarm. A ship arriving from our direction would not meet the galaxy all at once. It would encounter outlying structure first, then satellites, then the thin outer reaches of the disk, and only much later anything resembling the bright spiral that shows in photographs. Arrival at a galaxy is not an event. It is a gradual change in what surrounds you. Our own galaxy is about 100,000 light-years across through its stellar disk. Set that measurement against the gap, and the proportions become clear. The distance to Andromeda is roughly 25 times the full width of the Milky Way, edge to edge. A traveler crossing it would clear the entire span of our galaxy, then do it again and again, 25 times over, before arriving. Within a galaxy, stars are close enough that light crosses from one to the next in a handful of years. Between galaxies, there is nothing of the kind. The gap is not a longer version of interstellar space. It is a different kind of emptiness with a different scale attached to it. Our galaxy does not truly end at the disk, however, and neither does Andromeda. Beyond the stars lies a halo of hot, extremely thin gas, known as the circumgalactic medium, and it extends outward for hundreds of thousands of light-years in every direction. Beyond that, the dark matter halo reaches further still, unseen and unlit, detectable only by the way it bends the motion of everything inside it. A galaxy, defined honestly, is far larger than the bright part anyone photographs. The luminous disk is the dense core of something much wider and much fainter, and the boundary between a galaxy and the space around it is not a line but a slow fading. Because those halos are so extended, the two galaxies are in a sense already touching. Their outer envelopes of thin gas most likely overlap somewhere in the middle of the gap, which means that a ship crossing from here to there might never be entirely outside one galaxy or the other. The genuinely empty portion of the trip is shorter than the full distance. It is only slightly shorter, and the difference does nothing helpful to the schedule, but it changes the shape of the picture. The crossing is not a leap across a void with a wall of nothing in the middle. It is a passage from the dense part of one structure, through the thin outskirts of both, into the dense part of the other. The gap is not truly empty in any case. It holds thin ionized gas, sparse dust, and stars that were stripped out of both galaxies by earlier gravitational encounters. These intergalactic stars belong to no galaxy at all. They drift in the space between in numbers nobody has counted properly, each one carrying its own planets and its own light into territory where there is almost nothing to illuminate. A ship crossing the gap would pass a very long way from any of them. Still, the space between galaxies has residence, and that fact matters later, because thin material at high relative speed does not stay harmless. Andromeda is visible to the unaided eye from a genuinely dark sight. It appears as a faint, elongated smudge, easy to miss and easy to mistake for a flaw in one's vision. What reaches the eye in that moment is light that left the galaxy about 2.5 million years ago, before our species existed, when the ancestors of modern humans were still working out how to shape stone. The light has been in transit the entire time since. Nothing about it has changed on the way, and nothing about it is current. It is the oldest thing most people will ever see with their own eyes without knowing they are seeing it. That has an odd consequence for anyone planning a crossing. The galaxy is not observed as it is, but as it was, and the difference between those two states is exactly the size of the gap that must be crossed. The observation and the destination are separated by the same distance. A telescope pointed at Andromeda is looking at a 2.5 million-year-old report, and any traveler heading there is aiming at a place that will have moved, turned, and aged by the time of arrival. The stars picked out as a destination today are not where they appear to be, and some of them will not be there at all. The two galaxies differ in their centers as well. Andromeda's central black hole is far more massive than our own, on the order of 100 million times the mass of the Sun, against roughly 4 million for the Milky Way. That is a difference of more than a factor of 20, and it reflects a different history of growth, mergers, and feeding. Neither object is a hazard to a visitor at any sensible distance. A black hole exerts no more pull than any other mass of the same size. They are simply the anchors that each galaxy has assembled around, and they are one of the clearest signs that these two spirals, which look like siblings from a distance, have not lived the same life. There is one further fact about the gap, and it is the reason the whole question has a deadline of a sort. Andromeda and the Milky Way are on a collision course. The approach at 110 kilometers per second is not a passing motion but a fall, and the two galaxies will eventually meet, pass through one another, and merge over a span of hundreds of millions of years. That event is scheduled for roughly 4 billion years from now, which is far beyond any crossing timescale worth discussing. The gap is closing on its own. It is simply closing far too slowly to be of any use to anybody, and slowness, as it turns out, is the shape of nearly every problem that follows. Part 2. Setting the clock. A gap of that size only becomes a real problem when it is converted into time. Distance alone is inert. It is the crossing time that decides whether a plan is a plan or a wish. 3 broad speed regimes are available, in principle or in practice, and all 3 produce crossing times that break the plan in a different way. Working through them in order does something useful. It sets the clock that every later hazard in this crossing runs against, because none of those hazards matter in themselves. What matters is how long the ship is exposed to each one. The first regime covers what has actually been built and flown. Our fastest departing probes, the handful of craft on escape trajectories out of the solar system, are moving away at roughly 17 kilometers per second. That is quick by any earthly standard, and slow by the standard of the gap. At 17 kilometers per second, the crossing to Andromeda takes on the order of 44 billion years. The current age of the universe is a little under 14 billion years, so the trip would take more than 3 times as long as everything that has happened since the beginning. The sun will have died, cooled and faded, before such a ship was a fraction of the way across. This is the honest starting point, and it is the reason nobody proposes it seriously. The fastest object we have ever accelerated did rather better, and did it by cheating. It reached roughly 190 kilometers per second, more than 10 times the speed of the departing probes, and it achieved that not by carrying fuel, but by falling toward the sun. Gravity did the work, as gravity always does it, for free, and only in the direction the sun happens to point. That is more than 10 times faster than anything heading outward, and it still leaves a crossing time of about 4 billion years. 10 times the speed buys a tenth of the duration, and a tenth of 44 billion years is not a schedule anyone can use. The arithmetic here is stubborn in a particular way. Improvements that feel enormous barely move the number. The trouble sits in the way rockets work, and the principle is simple, even though the algebra is not. A rocket moves by throwing something backwards, and the faster it can throw that something, the more speed it gains for each kilogram thrown. Chemical rockets, the kind that lift everything off Earth, throw their exhaust away at roughly 4.5 kilometers per second. To go much faster than the exhaust, a rocket must carry an enormous amount of propellant, and that propellant has weight, and the rocket must then carry fuel to accelerate its own fuel. The requirement does not grow gently. It compounds, so that each additional increment of speed costs several times what the previous one cost. Beyond a certain point, the ship is almost entirely fuel, wrapped around a payload that has become an afterthought. Better exhaust speeds exist. Ion and electric propulsion, which push out charged particles rather than burning anything, reach exhaust speeds somewhere around 30 to 50 kilometers per second, roughly 10 times better than chemistry can manage. The catch is thrust. These engines deliver a push so gentle that it would not hold a sheet of paper against gravity, and they must run continuously for years to build up a modest change in velocity. They are patient and efficient, and patience is exactly the resource this problem consumes fastest. Applied to a crossing of 2.5 million light-years, an efficient engine with almost no thrust is not a solution. It is the same problem moved slightly. Beyond what has flown, there are designs that have been studied carefully but never built. A nuclear pulse concept, which pushes a ship forward by detonating charges behind a heavy plate, could, in principle, reach several % of the speed of light. A fusion design of the sort examined for probes to the nearer stars might manage around 12% of light speed, which is genuinely fast, more than 30,000 kilometers per second, fast enough to cross from the Sun to its nearest neighbor star in a few decades. At 12% of light speed, Andromeda is roughly 21 million years away. The improvement over chemical rockets is a factor of thousands. The crossing time is still longer than the entire history of our genus by a factor of hundreds. A laser-driven light sail does better still and gives up more to get there. The idea is to leave the fuel at home. An enormous laser array in the solar system pushes on a mirror-thin sail, so the ship carries no propellant at all. Such a sail could in principle reach 20% of light speed, but only for payloads measured in grams. No crew, no shielding, no instruments beyond the barest minimum, and no way whatsoever to slow down at the far end. Even with all of that given up, the crossing runs about 12.5 million years. The fastest thing anyone has seriously designed still needs longer than the time separating us from the earliest apes. Antimatter is where the energy argument runs out of room. It is the highest energy fuel physically available, converting mass entirely into energy with nothing left over, which makes it hundreds of times better than fusion and billions of times better than chemistry. Two problems stand in the way, and neither is small. Global production of antimatter is measured in nanograms per year, quantities so small that the entire supply ever made would not power a household appliance for long. And when antimatter annihilates, most of what comes out is gamma radiation, which passes through matter rather than pushing against it. Directing that energy into thrust, rather than letting it cook the ship, is an unsolved engineering problem of its own. Relativity offers the one genuine escape, and it is worth being precise about what it does and does not give. At high enough speed, time aboard the ship runs slowly compared with time outside it, so the traveler's own experienced crossing shrinks. At 99% of the speed of light, the trip to Andromeda takes about 2.5 million years, measured by outside clocks, but only around 350,000 years for anyone aboard. That is a real reduction by a factor of 7, and it is not an illusion. The crew would age by the smaller amount. It is also, plainly, still not a human lifetime. 99% of light speed is not nearly close enough to light speed to matter here. Compressing the experienced crossing into something a crew could live through would require a time dilation factor in the tens of thousands, and that is where the energy figures stop being negotiable. Reaching that regime demands a kinetic energy of about 1,000 billion joules for every single kilogram of ship. For a vessel of 1,000 tons, modest, roughly the size of a large ocean-going ship, and almost certainly too small for a self-sustaining crew, the total comes to something like a billion joules. That is comparable to several million years of total human energy production. Every power station and engine and fire on the planet poured into accelerating one ship. And that figure is only for speeding up. It says nothing about stopping. The rocket equation returns at this point and makes the picture worse. Carrying fuel aboard for both the acceleration and the deceleration at those speeds implies fuel-to-payload mass ratios in the billions, and that is assuming perfect antimatter conversion with no losses at all. Real drives are not perfect. A realistic engine wastes most of what it consumes as heat, and heat in a vacuum can only be shed by radiating it away, which requires radiator surfaces of a size that quickly rivals the ship itself. Waste heat becomes a hard constraint entirely separate from the fuel. A drive powerful enough to matter is also a drive powerful enough to cook whatever it is attached to. Slowing down is the half of the problem that is usually left out of the conversation. A ship that cannot decelerate does not arrive anywhere. It passes through Andromeda at a fraction of light speed, crosses the entire galaxy in a few 100,000 years, and continues into the dark on the far side without ever having stopped. Braking against the surrounding medium does not help, because the intergalactic gap is far too thin to push against. Magnetic sails and scoop designs that work on paper have nothing to grip. A laser array at the destination could slow a sail down, but building one requires the destination to be settled already, which is the thing the trip was meant to accomplish. There is one last point worth holding on to before moving on. Time dilation is a private benefit. It shortens the crossing for the crew and for no one else, because the galaxy they left still ages by the full 2.5 million years, regardless of what their own clocks report. Whatever sent them will not be there. Whatever they were sent to do will have stopped mattering. So the clock is set, and it reads somewhere between a few 100,000 years and several billion, depending on how generous one is willing to be, about engines that do not exist. Every hazard that follows in this crossing runs against that clock, and every one of them is slow. Part 3. The point of no return. Those crossing times describe the journey as it looks from outside, compressed into a single figure. The journey itself does not begin that way. It begins with a few hours that would strike almost any observer as uneventful, and that quiet is worth examining closely, because the departure of an intergalactic ship is the least dramatic moment in the entire undertaking. There is no boundary to cross, no threshold that announces itself. There is only a slow accumulation of velocity, and behind it, a set of conditions that quietly stop being negotiable. Acceleration is the first thing constrained, and it is constrained by the body rather than by physics. A human frame tolerates about 1 gravity indefinitely, because that is the load it evolved under. Higher sustained accelerations are survivable for hours and tolerable for days, but they impose steady cardiovascular strain, and no crew could endure them for the length of a crossing. So 1 gravity becomes the working ceiling, not because engineers chose it, but because the passengers are made of the material they are made of. It is a comfortable number. It is also, by an enormous margin, beyond anything that has ever been built. The reason is worth stating plainly. A ship holding 1 gravity of acceleration continuously would approach light speed within roughly a year of its own time. That is not a limitation of the human body at all. It is a statement about how much energy the drive would have to deliver, second after second, for month after month. Every propulsion system ever flown produces its acceleration in brief pulses, or produces a thrust so faint that it must run for years to change a velocity meaningfully. Sustained thrust at one gravity is not a comfort problem. It is an energy problem, and it is the same energy problem that sets the crossing time in the first place. Assume it's solved. Assume the ship is underway. The first thing that changes is not physical, but conversational, and it changes almost immediately. Radio travels at light speed, and light speed is generous inside a solar system and miserly outside one. While the ship is still within a few light hours of home, a question and its answer are separated by a delay that is awkward but workable. Within a few light days, that same exchange takes more than a week. Conversation stops being conversation and becomes correspondence. Then correspondence becomes broadcast, because there is no longer any point in waiting for a reply before speaking again. At 1,000 light-years out, still a small step across the Milky Way and no distance at all on the scale of the crossing, a message sent home and the reply to it consumed 2,000 years between them. Whatever institution launched the ship will have dissolved long before that reply is composed. Whatever question the crew asked will have been answered by people who never knew them, in a language that has drifted, on behalf of an organization that no longer exists in the form that signed the launch order. The link is technically intact. It has simply stopped connecting anyone to anyone. The physical side of the link fails on its own schedule. Signal strength falls with the square of the distance, so a transmitter adequate at the edge of the solar system is hopelessly faint a few light-years out, and unusable long before the galaxy's edge. Antennas can be made larger and receivers more sensitive, but neither scales fast enough to keep pace with the square of a growing number. Even one-way telemetry, the ship reporting home with no expectation of an answer, becomes impractical while the crossing is still in its earliest fraction. The silence is not chosen. It is arithmetic. Behind the loss of contact sits a second absence, and this one has no technical remedy at all. There is no rescue architecture beyond the inner solar system. Nothing exists that could reach a vessel in trouble a few light days out, and nothing conceivable could reach one in the gap between galaxies. Every rescue that has ever been performed in space has depended on a nearby vehicle, a short transit, and a planet close enough to fall back toward. Remove all three, and the concept itself no longer applies. Whatever goes wrong aboard, the people aboard will fix it, or they will not. There is no third outcome, and the crew knows this before the drive is lit. That principle extends to matter as well as to help. Every liter of water, every gram of food, every spare valve, seal, bearing, and circuit board is fixed at the moment of departure. Nothing can be added later. This is why the ship must carry its own atmosphere, its own water cycle, its own food chain, and its own waste processing as closed loops, each of which must run without net loss for the whole crossing. The largest closed ecological system ever built on the ground struggled to hold its air chemistry stable for a matter of months, with a planet's worth of engineers standing outside it. The ship has no outside. Its air, its water, and its living matter are the same finite inventory circulating through different forms, and every leak, every seal that weeps a little, every gram that plates out on a cold surface and is never recovered, subtracts permanently from a total that cannot be topped up. Steering is the next thing to become expensive, and it becomes expensive in a way that is easy to overlook. At low speed, a course correction is a modest expenditure. At relativistic speed, changing direction means changing a velocity vector whose magnitude is already an appreciable fraction of light speed, and the energy required for a meaningful turn approaches the energy that produced the original acceleration. A ship traveling at a large fraction of light speed is not maneuverable in any useful sense. It is aimed. Whatever aim it was given at departure is very close to the aim it will keep. Aiming, in turn, is not a matter of pointing at what can be seen. The ship must be directed toward where the target region of Andromeda will be when it arrives, not where the light now leaving it suggests it is. Andromeda approaches at roughly 110 kilometers per second. Its own stars orbit within it at hundreds of kilometers per second, and the arrival time is measured in millions of years. The aim point is therefore a prediction stacked on a prediction. Launch windows, by contrast, are irrelevant. On any timescale a human institution can plan within, the target does not move enough to matter. There is one further condition that departure quietly settles. A vessel large enough to carry a closed ecology, deep shielding and a drive of the required class cannot be launched from a planetary surface at all. It has to be assembled in orbit, which makes the departure the end of an industrial program lasting decades and consuming the output of an entire civilization's space infrastructure. By the time it leaves, the ship is not a spacecraft in the ordinary sense. It is a fragment of a society, and the society that built it has already spent generations arranging its exit. Abort remains possible for a short while. In the first weeks, a ship that has retained enough propellant to reverse its acceleration could still turn and come home, and the crew would arrive to a world that remembered them. But retaining that propellant means carrying it the entire way and never using it, and the mass budget of any realistic mission profile will not permit the reserve. The abort option is therefore not removed by an event. It is removed by a decision taken years earlier, on paper, by people calculating fuel fractions. It expires quietly, on a schedule, and nobody aboard feels it go. Somewhere in the first year or two, the ship also passes out of the heliosphere, the bubble of solar wind that partially deflects lower energy charged particles throughout the solar system. Nothing marks the transition. Instruments record a change in particle counts and magnetic field direction, and that is all. But the ship has crossed from a sheltered volume into an unsheltered one, and it will not be sheltered again for the length of the crossing. This is the pattern that departure keeps repeating. Protections do not fail. They are simply left behind, one after another, without incident. That is the whole character of the beginning. The crew is comfortable. The systems are new and running well. The sun is still bright enough to cast shadows, and the view is not yet strange. Nothing in the first hours registers as hazardous, because nothing in the first hours does anything. Departure is dangerous entirely in what it subtracts: the possibility of rescue, the possibility of resupply, the possibility of an answer, the possibility of turning around. Before it, the people aboard are a population with options. After it, they are a population with a schedule, and the schedule runs for a very long time. Part 4. The emptiness between. Beyond the heliosphere, and then beyond the galaxy itself, the ship enters the emptiest environment that physically exists. It is worth being precise about what that emptiness contains, because the intergalactic gap carries a reputation it does not entirely deserve. In most respects, it is the gentlest stretch of the whole route. In a few specific respects, it is the least forgiving. The asymmetry between those two statements is one of the more genuinely counterintuitive facts in the subject, and it is worth taking slowly. Start with the space the ship is leaving. Inside the disk of the Milky Way, the interstellar medium averages roughly 1 atom per cubic centimeter. That average conceals an enormous range. In hot, evacuated bubbles carved out by old stellar explosions, the density drops to a small fraction of an atom in that same volume. In cold molecular clouds, It climbs to hundreds or thousands of particles per cubic centimeter, and in the dense cores where stars form, it climbs far higher still. By any laboratory standard, even the densest of these is an excellent vacuum. By the standard of what lies outside the galaxy, all of it is thick. The intergalactic medium averages roughly 1 atom per cubic meter. That is about 1,000,000 times thinner than the space between stars in our own galaxy. The comparison is easier to hold if it is put in terms of volume. A region that would hold a single atom out in the gap holds 1,000,000 atoms inside the disk. And the gap is not uniformly at its average. In the deepest cosmic voids, the enormous underdense regions between the filaments of large-scale structure, the density falls further still to a fraction of a single atom per cubic meter. There are volumes the size of a house out there that contain nothing at all. The little that is present is mostly hydrogen and mostly ionized, stripped of its electrons, existing as bare nuclei and free electrons rather than as intact atoms. It is too diffuse to emit visible light in any quantity, so it is invisible in the ordinary sense. A large fraction of the universe's ordinary matter sits in this state, in what is called the warm-hot intergalactic medium, at temperatures somewhere between 100,000 and 10 million degrees. It is detected chiefly by what it removes. The light of distant bright objects passing through it arrives imprinted with a forest of narrow absorption features, each one a record of gas the beam happened to cross on its way here. Those temperatures sound alarming, and they are not. Temperature at these densities is one of the most misleading numbers in astronomy. Temperature describes how fast the individual particles are moving, not how much heat is available to transfer. A gas at 1,000,000 degrees with 1 atom per cubic meter carries almost no heat energy in any practical sense, because heat moves by collision, and collisions are almost entirely absent. A hull passing through such a gas would not warm. It would be struck by a few extremely energetic particles per second and would otherwise notice nothing at all. The same absence of collisions works against the ship in one direction. Because there is effectively no medium to conduct or convect heat away, the vessel cannot cool the way objects cool in air or water. It can only radiate, shedding energy as infrared light from its surfaces, and radiation is a slow way to move a large amount of heat. A high-powered drive therefore requires radiator area out of all proportion to the ship itself. The gap is the coldest place available anywhere. The microwave background that fills it sits at about 2.7 degrees above absolute zero, and nothing colder occurs naturally, and yet a ship inside it can still overheat, because being surrounded by cold is not the same as being able to reach it. Then there is the matter of speed, which changes the character of the medium completely. At ordinary velocities, a thin gas is simply a thin gas. At a large fraction of light speed, the ambient atoms become, from the ship's point of view, a directed beam of particles arriving head-on. A hydrogen nucleus that is essentially stationary in space arrives at half light speed, carrying tens of millions of electron volts of energy. That is squarely in the range of a particle accelerator, and the ship is flying into a continuous, unavoidable beam of it for the entire crossing. Here is where the emptiness earns its place. The intensity of that beam depends on how many atoms the ship sweeps up per second, and that depends directly on the density of the medium. Because the intergalactic gap is about 1,000,000 times thinner than the interstellar medium inside a galaxy, the beam is about 1,000,000 times weaker than the equivalent beam would be inside the disk. The same crossing, made at the same speed through galactic material, would present a particle flux that no plausible shielding could handle. Made through the gap, it is a manageable engineering problem. The emptiness genuinely helps, and it helps more than almost anything else on the route. One consequence of high speed is subtler. The microwave background is uniform and cold when measured from rest, but a ship moving through it at a large fraction of light speed sees it blue-shifted ahead and red-shifted behind, concentrated into a forward-directed glow. At modest relativistic speeds, this is merely a curiosity of the view. At extreme speeds, the blue shift is severe enough to push that ancient light up into ionizing energies, so that the coldest radiation in the universe becomes, from the ship's frame, a source of hard radiation streaming in from directly ahead. The universe's gentlest background is only gentle to those moving slowly through it. Dust is the exception to all of this, and it is a serious one. A dust grain is not a single atom. It is a solid particle, and a solid particle carries far more mass. At half light speed, a grain weighing a single microgram delivers kinetic energy comparable to the detonation of several kilograms of high explosive, concentrated into a point on the hull. There is no material that survives that impact as a surface. The only workable approach is to place a sacrificial shield far ahead of the ship on a boom, so that the resulting cone of vapor and debris has room to spread out before it reaches anything that matters. Intergalactic dust is extraordinarily sparse, far sparser than the dust inside a galaxy, which is itself thin enough that starlight crosses thousands of light-years through it. But sparse is not absent, and the crossing is not brief. Over a route of 2.5 million light-years and a duration measured in millions of years, the integrated number of encounters is not zero. This is the one hazard of the gap where the arithmetic of a long crossing works against the ship rather than for it, because a single sufficiently large grain is enough, and the probability of meeting one accumulates steadily with every year of flight. Leaving the galaxy removes something else that is easy to forget, because it has always been there. The Milky Way carries its own magnetic field, threaded through its disk, weak by laboratory standards, but enormous in extent, and that field scatters and partially deflects lower energy charged particles arriving from outside. Beyond the galaxy, that modulation disappears. Charged particles in the gap travel more nearly in straight lines, and whatever arrives unfiltered. The gap gives with one hand and takes with the other, a million-fold reduction in the amount of matter, and the loss of the only large-scale shielding structure the ship has ever been inside. The gap is also not the featureless void the word suggests. Filaments of the cosmic web thread through it, strands of gas and dark matter along which galaxies are strung, and the Milky Way and Andromeda sit on a common filament, which is part of why they are bound to each other at all. Scattered through the space between are stars stripped from their galaxies by past encounters, whole globular clusters wandering unattached, and isolated planets ejected from the systems that formed them, drifting without any sun. None of it is dense enough to constitute traffic. All of it means the gap is populated rather than truly empty. The densest sections of the route are the two ends. Each galaxy is wrapped in a circumgalactic medium, a halo of gas extending outward for hundreds of thousands of light-years, far denser than the true gap and far hotter. The ship crosses one on the way out and the other on the way in. Those halo passages, not the long middle, are the hardest sections of the crossing, and they bracket it, a difficult beginning, an easy majority, and a difficult end. What the middle offers instead is a problem of orientation. There is no meaningful navigation reference out there. Both galaxies are diffuse smudges of light at that range, their individual stars unresolvable for most of the journey, and there is nothing nearby to measure against. Position must be inferred rather than observed, carried forward by dead reckoning across millions of years. The ship is not lost, exactly. It simply travels through a region that offers it nothing to look at, at a density so low that the environment is best described by what it fails to do, which is nearly everything. Part 5. What crosses the emptiness? The gap between the galaxies is empty of matter in any ordinary sense, but it is not empty of motion. Something crosses it constantly, from every direction, at speeds very close to that of light. Galactic cosmic rays are bare atomic nuclei, stripped of their electrons and accelerated by violent processes scattered across the universe. They have been traveling for a long time before they reach anything, and they arrive with no preferred direction at all. That last detail matters more than it first appears, because a ship cannot turn a thick side toward the threat. There is no thick side. The flux comes from everywhere, and shielding one face simply leaves the others open. The composition of that flux is well measured. Roughly 87% of it is protons, the naked nuclei of hydrogen atoms. About 12% is helium nuclei, 2 protons and 2 neutrons traveling together. The remaining 1% is everything heavier: carbon, oxygen, neon, silicon, and, most consequentially, iron. That final 1% is small in number and disproportionate in effect, and it is the part of the spectrum that makes radiation a genuine engineering problem rather than a bookkeeping one. A proton passing through tissue leaves a thin, sparse trail of ionization behind it. Most cells it crosses are not seriously disturbed, and the ones that are can usually repair themselves. An iron nucleus behaves differently. It carries 26 units of positive charge, and the energy it deposits along its path scales with the square of that charge. The result is a dense, continuous column of ionization through every cell it enters, severing both strands of the molecular machinery at once and leaving damage the cell cannot cleanly stitch back together. A single such track can cross dozens of cells in a row, and it damages each of them along the way. The dose rates involved are known reasonably well from instruments carried outside the protection of a planetary magnetic field. They run on the order of half a millisievert to nearly 2 millisieverts per day, depending on how much mass surrounds the detector and on the state of the solar cycle. Over a year, that accumulates to a few hundred millisieverts. Natural background radiation at the surface of Earth runs at about 2 or 3 millisieverts a year, which puts the deep space environment at roughly 100 times the exposure a body receives simply by existing at home. An acute whole-body dose of around 5 sieverts, delivered in minutes, is lethal to about half of those who receive it without medical care. A crossing lasting 1,000 years accumulates hundreds of sieverts. The arithmetic looks conclusive, and it is worth being precise about why it is not quite as conclusive as it looks. Delivered slowly, radiation is far more survivable than the same total delivered at once, because living tissue repairs itself continuously. Enzymes patrol the damaged molecules, cut out the broken sections, and rebuild them. At low rates, that repair keeps pace. What it does not do is keep pace perfectly, and the errors it leaves behind are permanent. Repair capacity also varies by tissue, and the tissues that renew themselves least readily are the ones that keep the damage longest. Those errors accumulate as raised cancer risk, but that is not the only concern. Damage to the central nervous system from heavy nuclei is treated as a separate problem entirely, because nerve cells are not replaced the way most tissue is. Animal work suggests measurable changes in learning and behavior after exposures comparable to a long transit. Crews working outside a planetary magnetic field routinely report seeing brief flashes of light with their eyes closed, produced by single cosmic ray tracks passing directly through the retina. It is a quiet reminder that the flux is not an abstraction. It is arriving, individually, all the time. The obvious response is shielding, and the obvious form of shielding makes the problem worse. A high-energy nucleus that meets a sheet of aluminium does not simply stop. It shatters, and the target nucleus shatters with it, and the fragments continue forward as a spray of secondary particles, including neutrons that are themselves difficult to stop. A thin metal hull can deliver a larger dose to the crew inside it than no hull at all. The effect is well understood, and it is why shielding effectiveness is quoted in grams per square centimeter rather than in thickness. What matters is how much mass sits in the path and what that mass is made of. Hydrogen-rich material works best because hydrogen nuclei are single protons with nothing to fragment into. Water, polyethylene, and the ship's own stores of food and fuel all shield better per kilogram than metal does. Water has the additional virtue of being useful for other reasons. It is drinking supply, it is thermal mass, it is a chemical reserve, which is why most serious designs bury the crew compartment inside the water tanks rather than adding shielding as a separate structure. The difficulty is quantity. Effective protection means meters of it, wrapped around the habitable volume in every direction, and mass is the one commodity a propulsion budget cannot spare. Every kilogram of shielding must itself be accelerated to cruise speed, and in most plans, decelerated again at the far end. Shielding is therefore not a fixed cost, but a multiplied one, paid twice over in propellant, and it competes directly against the consumables that keep the crew alive. Other approaches have been proposed and none of them are ready. An active magnetic shield would generate a field around the ship to deflect charged particles before they arrive, which is roughly what a planet does. The field strengths and continuous power draw required are far beyond anything that has been built. A storm shelter is a smaller, heavily shielded compartment the crew retreats into during an acute event, and it is a sound idea for a journey between planets. It does very little for a crossing, because a crossing is not threatened by events. It is threatened by the continuous background, which is present in the shelter and outside it alike. Some of the news is genuinely better than expected. Solar particle events, the sharp and dangerous bursts that dominate radiation planning for travel between the planets, do not occur in intergalactic space. There is no nearby star to produce them. Low-energy galactic cosmic rays are partly confined by galactic magnetic fields, which means their flux in the deep gap between the galaxies is somewhat lower than it is inside the disk of a galaxy. The very highest energy component is unaffected and passes through everything, but the softer part of the spectrum thins out. The crossing is, in this narrow respect, a slightly quieter place than the neighborhood it departs from. The ship, however, brings its own source with it. Any drive capable of moving a crewed vessel between galaxies releases enormous energy, and both fusion and fission release a substantial share of that energy as neutrons and gamma radiation. A reactor irradiates its own crew unless it is separated from them by distance, by mass, or by both. The standard solution is a long boom and a shadow shield, a wedge of dense material placed between the reactor and the habitat. It works, and it costs mass, and it constrains the geometry of the entire vehicle around a single requirement. Radiation also damages the ship itself, and the ship cannot repair anything. Semiconductors accumulate total ionizing dose until their switching behavior drifts and then fails. Metals exposed to prolonged neutron flux swell, harden, and become brittle, losing the ductility that lets a structure survive a load it was not designed for. Polymers break down at the molecular level, so seals stiffen, adhesives lose grip, and insulation cracks. Over a century, the effects are manageable with spares. Over 1,000 years, every component the crew depends on is being slowly rewritten by particles they cannot see. There is one further gap in the picture, and it is an honest one. The combined effect of chronic low-rate radiation and continuous weightlessness on a human body has never been characterized because it has never been observed over anything close to the relevant timescale. Each stressor has been studied on its own, in short exposures, on small numbers of people. Whether they simply add together or make each other worse is unresolved. It is a real hole in the knowledge, and it is not the kind of hole that can be filled by argument. So the accounting on radiation comes out like this. It is real, it is cumulative, and it is eventually lethal without any ambiguity at all. Over a decade it raises risk. Over a century it is fatal to an unshielded crew. Over the timescales an actual crossing demands, it is beyond discussion. No amount of shielding brings hundreds of sieverts down to something a body absorbs and continues. And yet, of everything that threatens a crossing to Andromeda, radiation is not the first thing to reach you. It is patient. It works by accumulation, and accumulation requires time, and there are things aboard that will not wait that long. Part 6. The body without weight. There is one hazard on this list that is not a projection. Weightlessness has been studied on real human beings, in real conditions, for real durations, and the findings are not estimates drawn from models. They are measurements taken from people who lived without weight for months at a time and then came home to be examined. That makes this the best understood item in the whole accounting, and the picture it produces is unusually clear. It is also, like radiation, slow. The skeleton is the first system to register the change. Bone is not inert scaffolding. It is living tissue that is continuously dismantled and rebuilt, and the rate of rebuilding is set largely by the loads placed upon it. Remove the load and the dismantling continues while the rebuilding slows. In continuous weightlessness, weight-bearing bone loses roughly 1 to 1.5% of its mineral density every month. The hip, the lower spine, and the heel lose fastest, because those are the bones that carry a standing body. For comparison, age-related bone loss on the ground runs at about 1% per year. The condition resembles accelerated osteoporosis, and it does not fully reverse. Crews returning after long stays regain much of what they lost over a period of years, but not all of it, and the internal architecture of the bone does not rebuild in quite the same pattern it had before. The mineral that leaves the skeleton has to go somewhere. It passes into the bloodstream and out through the kidneys, which raises the concentration of calcium in the urine and with it the risk of kidney stones. A stone is a minor problem near a hospital. Aboard a vessel with no possibility of resupply, it is a different order of event entirely. Muscle follows the same logic and moves faster. The muscles that atrophy first are the postural ones, the calves, the thighs, the deep muscles along the spine, because those exist for no other purpose than resisting a downward pull. Without that pull, they are simply unused, and unused muscle is expensive tissue the body sees no reason to maintain. Strength in the legs can fall by 1/5 or more within a few months, and the fibers themselves change character, shifting toward a type suited to short effort rather than sustained standing. The loss is largely preventable with heavy resistive exercise, which is why crews in orbit spend around 2 hours of every day working against machines built to simulate load. 2 hours a day is affordable. It is also a requirement that never ends. The heart is a muscle as well, and it adapts to the same absence. On the ground, it works continuously against a vertical column of blood, pushing upward to the head and managing the return from the legs. In weightlessness, that column disappears and the workload falls. The heart becomes measurably more spherical, its walls thin slightly, and its efficiency as a pump declines. None of this is dangerous in orbit. It becomes dangerous only when weight returns, at which point a reshaped heart is asked to do work it is no longer trained for, and returning crews frequently cannot stand without assistance for the first day or so. The fluids themselves redistribute within hours. Roughly 2 liters of blood and interstitial fluid that normally pool in the lower body migrate upward and stay there. The visible result is the puffy face and the thin legs familiar from any long-duration crew photograph, along with persistent sinus congestion and a dulled sense of taste. The invisible result is more consequential. Pressure inside the skull rises and remains elevated, with no daily cycle of lying down and standing up to relieve it. The body has no mechanism for correcting a pressure difference that never goes away. That sustained pressure appears to act on the eye. Imaging of long-duration crews shows flattening at the back of the eyeball, swelling of the optic nerve head, and folds in the layers of the retina. The practical effect is a shift toward far-sightedness that in many cases does not fully resolve after return. A substantial fraction of those who have flown long missions show some version of it, and the severity broadly tracks the time spent weightless. It is one of the few effects that appears to worsen steadily with duration, rather than reaching a plateau, which makes it the most troubling item in the set for any journey measured in decades. The immune system becomes dysregulated in ways that are still being characterized. Certain classes of white blood cell shift in number and in behavior. The signaling molecules that coordinate an immune response drift out of their usual balance, and viruses the body normally holds in permanent check begin reactivating and shedding. Wound healing slows, and broken bone knits more slowly than it does on the ground. Taken together, this means an injury or an infection that would be routine at home becomes a more serious event in an environment where the medical capability is whatever was loaded before departure. The balance organs recalibrate as well. The inner ear reads acceleration, and with no constant downward reference, it rewrites its interpretation of what the head is doing. The adaptation takes a few days and produces nausea while it happens. It then has to be undone on return, producing the same nausea again in reverse. A crew arriving at a destination after a very long transit would be doing this recalibration with a vestibular system that had spent its entire functional life in weightlessness. Against all of this sits the size of the actual data set, and it is worth stating plainly. The longest single stay in orbit by one person runs a little over 14 months. A handful of others have passed a year. That is the entire body of direct human evidence on continuous weightlessness. A few dozen people, none of them beyond about 14 months, all of them exercising for hours a day, all of them within a few hours of an emergency return. Set that against a crossing measured in millennia, and the 14 months is a rounding error. Everything past it is extrapolation. The engineering answer is to supply weight by rotation, and rotation works. A spinning structure produces an outward force that a body inside it experiences as gravity, and the physics is entirely straightforward. The difficulty is the radius. Holding a full gravity at 2 rotations per minute, roughly the ceiling most people tolerate without persistent sickness, requires a radius of well over 200 meters. Spin faster and the radius shrinks, but 2 new problems appear. The apparent gravity differs noticeably between head and feet, so a person feels heavier standing than they do reaching upward. And every turn of the head produces a cross-coupled force the inner ear was never built to interpret, which is reliably nauseating. A rotating structure hundreds of meters across is also a machine, and machines have parts. Bearings must turn continuously without ceasing, under load, with no opportunity to replace them. Seals must hold pressure across a moving joint for the entire duration of the trip, since a rotating habitat joined to a stationary section leaks along that interface, or it does not leak at all. The structure must carry its own spin loads without fatigue cracking, and any shift of mass within it, crew moving, water tanks draining, cargo consumed, has to be balanced, or the whole assembly begins to wobble. All of this must survive without a maintenance visit for longer than any human structure has ever stood. Rotation solves the biology by adding a very large mechanical problem to the ledger. There is also a question nobody can answer, which is how much gravity is enough. There is no human data between weightlessness and a full gravity. A third of a gravity might prevent the losses entirely, or slow them by half, or barely help. The measurements have never been taken, so a designer choosing a partial gravity habitat to save mass and structure is choosing without evidence. It is worth noting one plain observation from animal biology. Hibernating animals lose far less bone and muscle than inactive animals that do not hibernate. What every countermeasure has in common is that it slows the losses without stopping them. Exercise regimes, resistive loading, pharmaceutical treatments for bone, rotation itself, each reduces a rate, and a reduced rate is still a rate. Over a century, the accounting arrives in the same place by a longer road. And this is the essential character of weightlessness as a hazard. None of it kills quickly. It degrades. A body held without weight for 100 years does not die of weightlessness. It becomes, gradually and without any particular moment of crisis, progressively less able to survive anything else that happens to it. Part 7. Why every plan ends in sleep. 6 hazards have been set out, and it is worth laying them side by side before going any further. The gap is 2.5 million light-years, and no part of that number is negotiable. The medium inside the gap is thinner than any vacuum ever produced on Earth, and it wears at a ship only across enormous spans. The radiation is constant and unhurried, delivering a dose that matters after centuries rather than after days. The body degrades gradually, in bone and muscle and vision and immune function, and each of those changes unfolds across years. The ship cannot be resupplied because there is nothing out there to resupply it with. And the crossing itself runs from roughly 12.5 million years at the outer edge of plausible engineering to something well past 40 billion years at the speeds actually achieved so far. What those 6 share is patience. Not one of them arrives quickly, and not one of them decides the outcome on its own. They set the conditions of the crossing rather than its ending. The plan is therefore not defeated by any single item on that list. It is defeated earlier, and by something considerably duller than radiation or distance. It is defeated by arithmetic. Consider a crew that simply stays awake for the whole duration. That crew must be fed, watered, and supplied with breathable air every single day of the voyage. It must be kept warm, kept lit, kept medically supported, kept occupied, and kept psychologically intact. None of those requirements ever pauses, and none of them can be deferred to the far end. A sleeping problem can be postponed, a waking one cannot. Every day of the crossing has a metabolic cost, and that cost is paid out of mass carried from the beginning. The numbers are not difficult. An adult consumes on the order of 800 grams of oxygen a day, several kilograms of water for drinking and hygiene, and something over half a kilogram of dry food. Together that is close to 5 kilograms per person per day, or under 2 tons per person per year. Across 10,000 years, a single crew member requires something in the region of 18,000 tons of consumables. For a crew of 100 that becomes nearly 2 million tons, before any structure, any shielding, any propellant, or any of the machinery that would hold it all together. And consumables are only the visible part of the load. Air filters clog and must be replaced, water processes foul, seals perish, pumps wear through their bearings, and medical supplies expire on shelves long before they are needed. Every one of those items is mass, and every one of them scales with the length of the voyage rather than with the size of the crew. Closed-loop life support reduces the figure, and reduces it enormously, but it never reaches the bottom of it. Water can be recovered from humidity, from wash water, and from urine at recovery rates approaching 90%. Oxygen can be regenerated from exhaled carbon dioxide, and carbon can be partly recycled through plants grown aboard. What no loop achieves is perfect efficiency. A cycle that returns 98% of what enters it still loses 2%, and the loss compounds every time the cycle turns. Over 10,000 cycles, an almost perfect loop is empty. Food is the part of the system that resists closure most stubbornly of all. Growing enough calories for one adult requires on the order of 40 to 50 square meters of intensively lit crop area, together with the power to light it, the water to irrigate it, and a soil or nutrient system that stays healthy indefinitely. A crop failure in such a system is not an inconvenience. It is a permanent reduction in what the ship can support. There is evidence for this rather than only theory. The largest closed ecology ever constructed on Earth sealed a small crew inside a glazed structure with soil, water, crops, and several engineered biomes. Within months, its oxygen concentration was falling faster than the designers had predicted, drifting down toward levels associated with altitude sickness. The oxygen was being taken up by microbes in the soil and by the curing concrete of the structure itself, and the carbon dioxide it should have produced was disappearing into the walls. The seal was eventually broken and outside air was added. That experiment lasted 2 years, under a sky, on a planet with an atmosphere available at the turn of a valve. The conclusion follows without drama. Mass is the universal currency of spaceflight, and every kilogram of crew support is a kilogram that must be accelerated at the start and slowed again at the end. At the speeds that make the crossing time tolerable, each kilogram carries an energy cost comparable to the annual consumption of a large nation. The awake crossing is therefore eliminated by mass long before it is ever eliminated by danger. It does not fail because the gap is hostile. It fails because the supply cupboard cannot be lifted. And the penalty is charged twice, since a ship that intends to stop at the far end must carry the means of stopping as well, and that propellant must itself be accelerated along with everything else. Adding mass to slow down means adding mass to speed up, and the requirement climbs faster than the payload it serves. That leaves 3 architectures that survive the arithmetic. All 3 have the same shape, and it is worth saying plainly what the shape is. In every case, the people who leave stop being awake. The first is induced torpor. The body is cooled moderately, by a handful of degrees rather than to freezing, and its metabolism is chemically suppressed until it runs at a small fraction of the usual rate. Oxygen demand falls, water demand falls, food demand falls, and waste production falls with them, roughly in proportion. That proportionality is the entire point, because it is where the mass saving comes from. A torpid crew also needs less volume, less lighting, less thermal comfort, and no provision for recreation at all. The crew remains alive, remains unconscious, and continues to age slowly for the whole crossing. Even a modest suppression changes the mass budget out of all recognition, because the saving multiplies across every day of a voyage counted in millions of years. The second is cryopreservation. Here the body is not slowed but effectively stopped, cooled far below freezing to temperatures at which chemical reactions cease to proceed at any meaningful rate. In principle, a crew held this way does not age at all, and the consumable requirement falls very nearly to zero. The ship then carries not a population but a cargo, and the entire life support problem collapses into a refrigeration and revival problem. In intergalactic space, the refrigeration is close to free, because the background temperature is under 3 degrees above absolute zero, and heat can simply be radiated away. The third is the generational architecture. The original crew lives awake, has children, grows old and dies aboard, and the ship is handed forward to descendants who inherit it the way people inherit a country. Nothing is frozen and nothing is suppressed. But this is still sleep, simply relocated from the individual to the mission. The people who set out go under in the ordinary way that everyone goes under, and they do not come back either. The ship arrives, if it arrives, carrying strangers. Its consumable problem is solved not by lowering demand, but by growing the supply aboard, which makes the closed ecology load-bearing for the entire crossing rather than merely helpful. Each of those three solves the mass problem convincingly. Each one, in solving it, transfers the entire risk of the crossing into a single step and makes that step unrepeatable. Some proposals try to hedge by alternating the sleep, keeping a small watch awake on rotation so that somebody is always available to intervene. That hedge reintroduces the consumable problem at reduced scale, which is manageable, and adds a new requirement that is not: every member of that watch must be brought back successfully, on schedule, again and again, for the length of the voyage. The supporting evidence for any of this is thin, and it is worth being honest about how thin. Everything known about people living in sealed, isolated, confined environments comes from polar stations, from submarines, and from analog habitats built for study. None of those has run for more than a couple of years. All of them sit inside a breathable atmosphere, and every one of them can be evacuated. There is no precedent at all for a sealed human community holding its structure across thousands of years, which is precisely the argument that pushes most planners away from generations and toward torpor. The alternative to an unproven biology is an unproven society. So the crossing does not begin with a hazard. It begins with a procedure. Before the ship has moved, before the medium has touched it, before a single particle of radiation has reached anyone, someone has to be put under. Every architecture that the arithmetic permits requires it, and there is no fourth option waiting behind them. The hazards catalogued so far all wait until the voyage is underway. This one is at the threshold, and it is passed through in the first hours. That procedure is the only element of the entire plan that has never once been performed successfully on a human being. Part 8. What the sleep actually does. No human being has ever been revived from cryopreservation. Not one, not partially, and not for a single moment. There is no case in the medical record of a person cooled to storage temperature and brought back, and there is no laboratory anywhere that claims otherwise. The procedure exists and is performed, and there are facilities holding bodies at low temperature at this moment. What does not exist is the second half of it. Every person currently stored is stored on the assumption that a technique which has not yet been developed will one day be developed by somebody else. Cooling itself is not the mystery. Clinical hypothermia is real, routine, and genuinely useful, and it is used in operating theaters and intensive care units to protect the brain when circulation is interrupted. But it cools patients only to around 32 to 34 degrees, a handful of degrees below normal, and it holds them there for hours or at most a few days. Even that shallow cooling carries a price. It disturbs heart rhythm, impairs the blood's ability to clot, suppresses the immune system, and raises the risk of infection. Doctors do it because the alternative is worse, and they warm the patient again as soon as they safely can. The reason cooling works is also the reason deep cooling fails. Chemistry slows as temperature falls, and below a certain point, it effectively stops. That is the entire goal, because a metabolism that has stopped consumes nothing, ages by nothing, and requires nothing carried aboard. But the chemistry of life is not the only chemistry running in a body. There is a second set of processes that repairs the first, continuously, every hour of every day, and cold does not distinguish between them. Stopping the damage and stopping the mending are the same act. Then there is the water. A human body is roughly 60% water by mass, and water expands as it freezes, by around 9%. Ice crystals forming inside a cell do not simply chill it. They grow, and as they grow they push, tearing membranes apart from the inside and rupturing the structures the cell depends on to function. Freezing between cells is nearly as damaging, because ice forming outside draws water out of the cells and leaves them shriveled in a concentrated salt solution. A body frozen without preparation is not preserved. It is destroyed, slowly and thoroughly, on the way down. The answer to ice is to prevent it from forming. Cryoprotectant chemicals, perfused through the circulation before cooling, interfere with the ordering of water molecules so that the tissue does not crystallize. Instead, it becomes steadily more viscous as it cools, until it stops moving altogether, without ever arranging itself into a lattice. The result is a glass rather than a solid, and the process is called vitrification. Vitrified tissue holds its structure at the molecular level in a way that frozen tissue does not, and the solutions used to achieve it are complex mixtures refined over decades for exactly this purpose. The difficulty is a matter of concentration. The amount of cryoprotectant needed to vitrify a whole human body is very large, and at those concentrations the chemicals are themselves toxic to the tissue they are meant to protect. They are most damaging at the warmer end of the procedure, which is precisely where they must be introduced, because perfusing them requires a circulation that still moves. So the procedure has to run a race it has never won, get enough of a poison into every cell to prevent ice, quickly enough that the poison has not already done the work the ice would have done. That tension is the central unsolved problem of the field, and it has been the central unsolved problem for a long time. Even setting it aside, the harder half is still to come. Rewarming is more difficult than cooling, not less. Warmed too slowly, a vitrified body crystallizes on the way back up, because the temperature range that the tissue passes through on the return is exactly the range in which ice forms most readily. The glass that was carried down intact turns to ice on the ascent and tears the tissue it was meant to preserve. The window in which this happens is narrow, and the rate required to pass through it is high. Warmed unevenly, the outcome is mechanical rather than chemical. Heat enters a body from the outside, so the surface expands while the interior is still rigid, and the stress builds across the boundary between them. Small samples tolerate this because heat reaches their centers almost immediately. Large organs do not, and they crack. This is not a subtle degradation of function. It is a fracture running through solid tissue, and no amount of subsequent care repairs it. There is active research into warming from within, using magnetic particles distributed through the tissue and heated uniformly by a radio frequency field, and it is aimed at precisely this problem. What has actually been achieved is worth stating carefully, because it is real. Small tissue samples have been vitrified stored and rewarmed successfully. More recently, individual animal organs have been carried through the whole cycle and shown to function afterwards. Those are genuine results, and they were hard-won. But an organ is a few hundred grams of relatively uniform tissue with a single circulatory inlet. A whole human body is many kilograms of profoundly different tissues, each with its own water content, its own tolerance, and its own perfusion, all of which must survive the same protocol at the same time. The gap between the two is not one of refinement. It is orders of magnitude. Nature offers a template, though not a solution. Ground-dwelling rodents and bears suppress their metabolism through winter, dropping heart rate and oxygen consumption to a small fraction of normal and surviving for months without eating. It is a real and well-studied capability. But those animals do not freeze. Their body temperature falls to a few degrees above the surrounding air and no further, and the chemistry inside them continues to run, slowly, the whole time. Months is not millennia, and cool is not cold. There is a further detail that makes the template less useful still. Hibernating animals do not stay under for the whole season. They rouse periodically, warming themselves back to normal temperature for a day or so before sinking again, and those arousals consume a large share of the energy the animal saved by hibernating at all. Nobody fully understands why, though the leading explanations involve repairing accumulated cellular damage and clearing waste that the slowed body cannot process. Nobody knows how to skip them. And humans have no such machinery to begin with. There is no dormant capacity in our physiology waiting to be switched on, because we are simply not a species that does this. Then there is the part that no amount of laboratory progress addresses. Cold does not stop radiation. A frozen body drifting through the gap accumulates the same dose as a warm one, particle for particle, across every year of the crossing. Nothing about being vitrified makes tissue less transparent to a cosmic ray. If anything, the arrangement is convenient in one direction only, since deep space is naturally cold enough to hold a body at storage temperature without any machinery at all. The cooling is free. It is the return that requires a working machine, running once, correctly, at the end of everything. The difference lies in what happens afterwards. A living body repairs radiation damage continuously, and that repair is why a slow dose is survivable when the same dose delivered at once is not. Repair enzymes are proteins, and proteins do not work at cryogenic temperature. Every strand break, every damaged base, every lesion is simply held in place and added to the one before it. The damage does not spread because chemistry has stopped. It also does not heal. It accumulates in a straight line for the entire duration of the voyage. And shielding cannot rescue this because a portion of the radiation is already inside. Natural potassium in human tissue includes a slightly radioactive form, and an average adult contains enough of it to produce several thousand decays every second, in muscle, in bone, in every organ. The carbon that makes up the body carries a radioactive fraction of its own, contributing thousands more. This has always been true of every human who has ever lived, and it has never mattered because the repair machinery clears the damage as fast as it appears. Take the repair away, and it matters immediately. There is no wall thick enough to shield a body from itself. Over 10,000 years, that internal contribution alone delivers a dose no tissue survives, without a single external particle being counted. Over 1,000,000 years, the question stops being medical. What remains is not a body in the chemical sense, only an arrangement of molecules that used to be one. So the sleeper is not preserved. The sleeper is taken apart, slowly and quietly, molecule by molecule, at a temperature too low to notice the damage and too low to mend it. The generational architecture reaches the same place along a gentler road, since the people who go under simply age and die in the ordinary way, and the question of arrival becomes a question about strangers. Whatever else the crossing does to a traveler, it does it afterwards, and it does it to someone who is no longer there to know. You never wake up. Part 9. The machine that cannot fail. Once the crew is unconscious, the hazards of the crossing change hands. Nothing that follows happens to a person who can notice it, report it, or respond to it. Every remaining danger becomes a danger to the vehicle, and the vehicle has no operator. There is no watch to stand, no inspection to run, no hand to reach into a panel and reseat a connector that has worked itself loose. The ship must hold its own course, carry its own power, keep its cargo cold, and at the far end perform the single procedure that has never once succeeded. It must do all of that alone. The record for machine endurance beyond the atmosphere is modest. Nothing humanity has built has operated in space for much more than half a century. The oldest craft, still returning a signal from the outer dark, were designed with working lifetimes, measured in a handful of years, and they have outlived those lifetimes by a wide margin. That is a genuine achievement, and it is not a precedent for anything longer. Half a century is not a conservative benchmark. It is the entire history of the attempt, with nothing beyond it. A crossing to Andromeda at a tenth of the speed of light asks a machine to run for roughly 25 million years, which is not a gap of 10 or 100 or 1,000. Engineering margins are built from experience with things that have already lasted, and here there is no experience to build from. Power fails first, and it fails on a schedule known in advance. Beyond a certain distance from any star, sunlight is far too thin to collect usefully, so the longest-lived craft in deep space carry their own heat source. A quantity of decaying isotope produces warmth continuously, and a converter turns a small fraction of that warmth into electricity. The arrangement has no moving parts, which is exactly why it lasts as long as it does. What it does not do is hold steady. The output falls year after year because the fuel is consuming itself by the only means available to it. A common fuel for this purpose loses half its output, roughly every 88 years. That decline is gentle at first and unforgiving in aggregate. After a few centuries, the craft is running on a fraction of its designed power, and instruments begin to be switched off in order of expendability. After 1,000 years, well under 1% of the original output remains. After 10,000 years, there is effectively nothing left, and 10,000 years is a rounding error against the length of this crossing. Loading more fuel at departure only moves the point at which the curve reaches zero, by an amount too small to matter. Fission offers a longer fuel life, and it is the obvious answer for anyone drawing the problem on paper. A reactor can in principle produce useful power for centuries rather than decades. The difficulty is what a reactor requires around it: pumps to move coolant, valves to direct it, radiators to reject waste heat, control systems to hold the reaction steady, and sensors to tell those systems what is happening. Every one of those is a mechanism, and mechanisms are precisely the components that time removes. A source with no moving parts decays predictably. A source with moving parts fails unpredictably, and the failure needs to happen only once. Keeping the sleepers cold, by contrast, is nearly free. The space between galaxies sits under 3 degrees above absolute zero, and a surface shaded from every nearby star will radiate its own heat away until it approaches that temperature on its own. No compressor is needed, no refrigerant loop, no continuous power draw. The cold is simply there, permanently, in unlimited supply, asking nothing. It is one of the few elements of the plan that the universe provides without charging for it. Waking them is where the accounting turns. Rewarming a body from cryogenic temperature demands a large and precisely delivered quantity of energy, applied evenly, at the correct rate, throughout tissue of varying thickness and composition. That machinery is complex. It is powered, it has moving parts, and it must survive the entire crossing in a state of perfect readiness in order to operate for a few hours at the very end. It is asked to work exactly once, correctly, after millions of years of doing nothing at all. Nothing ever built has been asked to sit idle so long and then perform without error on demand. Vacuum acts on machinery in ways that have no everyday equivalent. Two clean metal surfaces held in contact without air between them will gradually bond to one another because there is no oxide layer and no adsorbed gas keeping them apart. The effect is called cold welding, and it seizes hinges, latches, bearings and release mechanisms that have not moved for a long time. A mechanism that operates daily keeps its surfaces refreshed by use. One intended to operate once, at the end of the crossing, spends the whole journey pressed still against itself in exactly the condition that encourages the bond to form. Materials also leave themselves behind. Every polymer, adhesive and composite aboard releases a slow drift of molecules into the vacuum for as long as the material exists. Over long spans the composition changes, and with it the strength and flexibility measured before departure. Those molecules settle on the coldest available surfaces, which tend to be optics, sensors, and radiators. A camera slowly fogs. A radiator slowly loses its ability to shed heat. Lubricants pose the same problem from the other direction, since anything fluid enough to lubricate is volatile enough to evaporate away. Radiation does its own work on the structure. Across long exposures, the steady flux of high-energy particles displaces atoms within metals, and the accumulated displacement causes the metal to swell and to grow brittle. Polymers and adhesives are more sensitive still, because the bonds giving them their useful properties are exactly the bonds a passing particle is likely to break. A joint that flexed at departure becomes rigid, and a seal that was elastic becomes a crumbling ring of powder. None of this is dramatic while it happens. It is a slow rearrangement inside solid material at a rate no instrument aboard is watching. Electronics carry the hardest limit of all. Every ionizing particle that passes through a semiconductor deposits a small quantity of charge in its insulating layers, and that charge does not entirely clear. It accumulates as total dose, shifting the voltages at which transistors switch until the device no longer behaves as designed and then ceases to behave at all. Hardened parts push that threshold outward by a considerable factor, and the factor is finite. No electronic component has been qualified for thousands of years, let alone millions, because no test could establish it, and no understanding of materials would confidently predict it. Redundancy is the standard answer to component failure, and it is an excellent answer to the wrong question. Carrying 3 of everything protects against 3 independent failures, each arriving for its own unrelated reason at its own moment. It protects poorly against a common cause, which is a single condition degrading every copy at the same rate. Time is the purest common cause there is. Galaxies will continue to drift. The stars overhead may appear eternal, but the great web of galaxies is always in motion. When the first fails from accumulated dose, the others are already near the same threshold. Genuine self-repair would answer all of this, and it is a far larger undertaking than the phrase suggests. Replacing a failed part requires a spare, and carrying spares for millions of years moves the problem back one layer, because the spares are aging on the same shelf. Manufacturing a replacement requires raw feedstock, a furnace, forming equipment, precision measurement, and a system able to diagnose what broke and decide what to build. That is not a toolkit. It is a small industrial base running unattended, which is another closed system with its own wear and its own need for repair. Information proves no more durable than hardware. Magnetic and optical storage degrade over decades and centuries rather than millennia, and any physically etched medium still requires a working reader. The software governing the ship must remain not merely intact, but correct, and must remain interpretable by whatever eventually needs to interpret it. No human language has held stable for even a few thousand years without diverging past easy recognition. A set of instructions written at departure is asked to mean the same thing after a span in which every language that has ever existed would have changed beyond use. There is also nobody to call. Almost every long-duration craft that has survived a serious fault survived it because people on the ground diagnosed the trouble and sent a fix. That option depends on a signal round trip measured in hours and on an institution still existing to send it. Across 2.5 million light-years, a message takes 2.5 million years to arrive and as long again to return. The ship is not merely automated, it is unreachable. Each of these failures is survivable on its own. A power decline can be met by shutting down everything not essential, and a seized mechanism can be designed around with dry surfaces and magnetic bearings. Storage can be duplicated, shielding thickened, electronics hardened, margins widened wherever widening is cheap. What cannot be arranged is for all of them to be survived at once, for millions of years, by a system that receives no attention whatsoever. A single stuck valve in a thermal loop ends the mission, and across 10,000 years there is no particular reason a valve should not stick. That is the quiet center of the problem. The failure will not be sudden and it will not be observed. It will be a slow drift in a converter's output, a film thickening on a sensor window, a bearing that no longer turns freely. None of it will register anywhere. The people aboard are cold and unconscious and are not coming back to check. The machine that cannot fail is asked to not fail for longer than the species has existed, with nobody awake to notice that it already has. Part 10. The generational alternative. There is an alternative, and it has been proposed seriously for as long as interstellar travel has been discussed at all. If the sleep cannot be made to work, the crew simply stays awake. Nobody is frozen, nobody is chilled, nobody is asked to survive a procedure that has never succeeded. Instead, the ship carries a living community, and that community hands the mission down to its children, who hand it down again. The sleep does not disappear under this arrangement. It changes form, moving from the individual body to the society, and it lasts far longer than any body would. The arithmetic sets the scale before anything else does. At 1/10 of the speed of light, the crossing to Andromeda takes something close to 25 million years. A human generation runs to roughly 25 years, which means the ship must pass through a number of generations on the order of 1 million. That figure is worth sitting with, because it does not resemble a voyage in any ordinary sense. 1 million generations is not a long expedition. It is a period of time in which the passengers are not the point, because the passengers will be replaced 1 million times over before anything arrives. 1 million generations is an evolutionary span. It is considerably longer than the interval separating modern humans from ancestors we do not classify as our own species at all. Over such a period, populations change shape, change size, change the frequency of every heritable trait they carry, and change in response to whatever pressures happen to be acting on them. On a ship, those pressures are unusual and constant. A fixed gravity setting, a fixed light cycle, a fixed diet, a fixed and very small pool of possible partners. Whatever steps off at the far end will be descended from the crew that left. It will not be the same species in any biological sense, and it will not have been consulted about the change. Before evolution becomes the issue, simple population genetics does. Estimates for the minimum viable population of a closed human group run from the low hundreds into the low thousands, depending heavily on how carefully reproduction is managed. A group at the lower end can be made to work only with deliberate pairing schedules, careful record-keeping across generations, and a level of reproductive control that no human society has ever accepted voluntarily. A group at the higher end is genetically safer and physically far harder to carry. Every additional person multiplies the food, water, air, volume and waste processing that must be produced continuously for millions of years from a sealed inventory. Too small a founding population produces the familiar problems. Rare harmful variants that stay hidden in a large population begin to meet copies of themselves, and the result is a measurable decline in fertility, survival, and health across successive generations. Too large a population produces the opposite problem, which is not biological but structural. A ship sized for thousands of people is a ship that must be accelerated, shielded, and fed for the entire crossing. There is a narrow band between those two failures, and the plan requires the population to remain inside it, without external correction, for 1 million generations in a row. Genetic variation also drains away on its own. In any finite population, some variants are lost each generation purely by chance, because not everyone reproduces and not every gene is passed on. That process is slow, and it is relentless, and it operates even in a well-managed group with careful pairing. On Earth, the loss is offset by migration, by newcomers arriving with different ancestry, and by the sheer size of the wider population. Aboard a ship, there is nothing to offset it. The gene pool present at departure is the complete and final supply, and every generation it becomes slightly narrower than the one before. Frozen gametes are sometimes offered as the remedy, and they are a partial one. A stored bank of reproductive cells could reintroduce variation that has been lost, which is a real and useful capability. The difficulty is that it reintroduces the preservation problem in a smaller and more tractable form, not that it removes it. Those cells must survive the same span, at the same temperature, under the same accumulating radiation as everything else aboard. Embryo-carrying designs go further still, proposing that nobody makes the crossing awake at all. That approach moves the unsolved biology to the far end and requires a machine to raise and educate children with no adults present, which is not a smaller problem. The physical arrangements are demanding in their own right. Children do not develop normally in weightlessness. Bone, muscle, circulation, and the balance system all form in response to a load that is not there. Any generational ship must therefore rotate, producing an effective gravity through steady spin, and must sustain that rotation with the structural integrity to support it for the whole crossing. That adds mass, adds bearings, adds stresses that cycle continuously, and adds one more system that must never stop. A ship carrying sleepers can be a cold and motionless object. A ship carrying families cannot. Cultural continuity is a separate problem, and a harder one. Languages drift steadily, even in large, literate, connected populations, and an isolated group of a few hundred drifts faster. Within roughly 1,000 years, spoken language diverges to the point of mutual unintelligibility with its own earlier form. Written records slow that process but do not stop it, because the written form must still be taught by people who no longer speak it. After 10,000 years, the departure documents are ancient text in a dead language. After 1,000,000 generations, the idea that any message from the beginning still means what it meant is not a plausible assumption. Institutions do no better. No human organization has maintained continuous functioning operation for 5,000 years. The oldest surviving structures of governance and belief have all been broken, reformed, split and rebuilt many times over, and their present versions would be barely recognizable to their founders. A generational ship requires something stronger than any of them, an arrangement that holds a specific purpose intact, unbroken, and acted upon, across a span in which every civilization that has ever existed would have risen, changed beyond recognition, and ended several thousand times over. The purpose itself is the strangest part of the arrangement. The mission must be transmitted, understood, believed, and carried out by people who never chose it. They will not have seen the world that chose it for them. They will have no experience of open sky, weather, oceans, cities, or any of the reasons the crossing was thought worth attempting. To them, the ship is not a vehicle. It is the entire physical world, and the destination is a story told by people long dead about a place nobody aboard has ever seen and nobody aboard will ever reach. Everyone born on such a ship inherits a sealed environment, a fixed population, an assigned role, and no possibility of leaving. There is no frontier to move to, no other community to join, no way to opt out of a decision made before anyone alive was born. Any system of governance must handle succession, disagreement, crime, and the allocation of scarce resources with no outside arbiter and no exit available to anyone. A community that loses faith in the mission cannot abandon it, because the ship cannot stop, cannot turn, and has nowhere else to go. The disagreement simply continues, in the same corridors, for the rest of everyone's life. Underneath all of it sits the life support, which must run without interruption for the same span. A closed ecology has to be small enough to carry and complete enough to cycle every element the crew consumes, turning waste back into food, air, and water indefinitely. The largest closed ecology ever built on Earth was sealed with a small crew inside, and its oxygen concentration declined steadily for reasons that took a long time to identify. That was a modest structure, on a planet, with specialists outside, and a door. It still had to be opened. Small closed systems shift without warning. A species collapses because its food source declines. A chemical balance moves outside the band that keeps a cycle turning. A pollinator disappears, or a soil process consumes something nobody was measuring. On Earth, such shifts are absorbed by the size of the surrounding world. Something else moves in, and the system finds a new balance. Aboard a ship, there is no surrounding world to absorb anything. Whatever is lost permanently, and the crew must correct the imbalance using only what is already inside the hull. So the generational route does not remove the failure. It delays it and distributes it, spreading a single catastrophic problem across 1,000,000 generations so that no individual has to face all of it at once. Each crew inherits a slightly narrower gene pool, a slightly more drifted language, a slightly less stable ecology, and a mission that means slightly less than it did. None of those declines is fast enough to notice within one lifetime, which is precisely what allows them all to continue. And it answers the question of the episode in its own way, which is not a gentler answer. Under the frozen architecture, the sleep is what ends the crossing, and the ending is not observed. Under this one, nothing is skipped. The people who leave still never arrive, because the distance is far larger than any human life, and no arrangement of biology changes that. They simply stay awake while it happens, and they hand the not arriving to their children, who hand it on again, quietly, for as long as the ship holds together. Part 11. The destination will not wait. One assumption sits underneath every plan described so far, and it is quietly wrong. The assumption is that the destination holds still. Andromeda is not a fixed mark on a chart. It is a moving object built out of moving objects, and it is moving toward the Milky Way at roughly 110 kilometers per second along the line between them. That is not a small number by any measure a human body understands. It is faster than anything our species has ever launched, and an entire galaxy is doing it, continuously, without any prospect of stopping. Across the length of a crossing, that approach accumulates. A ship traveling at 1/10 of the speed of light would need something on the order of 25 million years to cover the gap, and Andromeda would spend those same 25 million years working the gap shorter from its own end. At 110 kilometers per second, a galaxy covers roughly 9,000 light-years in that span. The destination comes partway out to meet the traveler. It is one of the very few pieces of generosity this problem contains. It is worth being honest about the size of that gift. 9,000 light-years measured against 2.5 million is well under 1% of the total. The approach shaves a sliver off the crossing and changes nothing structural about it. Every hazard already described still runs for essentially the full duration, and every system aboard still has to survive essentially the full duration. The galaxy's motion toward us is real, it is helpful, and it is close to irrelevant at the scale where the decisions are made. The stars inside Andromeda are a different matter entirely, and they are where the real aiming problem lives. A galaxy is not a rigid body. It is a loose assembly of hundreds of billions of stars, each on its own orbit around a shared center of mass, each moving at a few hundred kilometers per second relative to that center. A star sitting at a galactic radius comparable to the Sun's takes on the order of 200 million years to complete a single circuit. That is the natural clock of a galactic disk, and it is slow only in comparison to everything else in this episode. 25 million years measured against a 200 million year orbit is more than 1/10 of the way around. Whatever star a mission selected as its target would, over the course of the crossing, travel more than 1/10 of the full circumference of its orbit before the ship arrived. It would not be where it was seen. It would be tens of thousands of light-years along its path, carried there by the ordinary rotation of the disk it belongs to. Aiming at where a star appears to be is guaranteed to miss by a distance larger than most of interstellar space. So the aim cannot be at a position. It has to be at a prediction. A mission would need to measure the target star's motion across the sky, resolve how fast it is moving and in what direction, and then project that motion forward by 25 million years to a place where nothing is currently sitting. Measuring motion across the sky is straightforward for nearby stars because they visibly shift against the background over decades. At 2.5 million light-years, the same physical motion produces an angular shift so small that it took the better part of a century of careful observation simply to establish which way Andromeda as a whole is drifting sideways. Every error in that prediction compounds. A small mistake in the measured sideways motion of a single star, multiplied by 25 million years of travel, becomes an arrival point thousands of light-years from anything intended. The ship cannot fix this on the way. Course correction requires propellant, and a vehicle that has already spent nearly everything it carried getting up to speed has nothing meaningful left with which to steer. The trajectory is chosen at departure, from measurements made at the extreme edge of what instruments can resolve, and then it is simply held. Suppose all of that goes right. Suppose the aim is good and the prediction holds. What the ship arrives in is a galaxy, which means it arrives in a place considerably more crowded and more energetic than the gap it just spent millions of years crossing. Andromeda's disk carries dense star fields toward its center, molecular clouds thousands of times denser than the general interstellar medium, and the expanding remnants of stars that have already exploded. Its central region holds a black hole of around 100 million solar masses, considerably heavier than the one at the center of the Milky Way. None of those features is a hazard in the way an obstacle is a hazard, because a galaxy remains overwhelmingly empty even at its densest. The difficulty is that they are hazards a ship cannot respond to. A vehicle arriving after millions of years of unattended flight has no capacity to survey the region it is entering, choose a safer approach, or slow itself to look. It carries whatever shielding it left with, pointed wherever it was pointed, and it meets whatever happens to be in front of it. A molecular cloud that assembled long after the trajectory was fixed is simply part of the arrival. The most immediate arrival problem, though, is the medium itself. Interstellar gas within a galaxy is thin by every ordinary standard and thick by comparison with the gap between galaxies, and a ship still moving at any appreciable fraction of the speed of light meets that gas as a continuous flux of high-energy particles arriving against the forward structure. This is the departure problem run in reverse, and it is worse, because at departure the vehicle was accelerating out of a thinning environment, and at arrival it is driving into a thickening one. Shielding that survived the crossing must now do its hardest work at the very end of its life. Set against all of this, it is worth stating plainly what Andromeda actually is, because the running theme of this episode depends on it. Beyond the local group, the situation is not difficult, it is closed. The expansion of space carries distant galaxies away from us, and the further away they are, the faster they recede. Past a certain distance, the recession outpaces anything a ship could ever do to close it, and the destination is not merely far, but permanently out of reach. Most of the observable universe already falls into that category. It can be seen, and it can never be visited. Andromeda is exempt from that, and the reason is gravity. The Milky Way and Andromeda, together with the Triangulum Galaxy, the Magellanic Clouds, and a few dozen smaller companions, form a gravitationally bound group. Inside a bound group, expansion does not apply. The mutual pull of the members holds them together, and, in Andromeda's case, actively draws them closer. That is why Andromeda approaches instead of receding. It is the only other large galaxy that will ever be gravitationally available to anyone standing here, which makes it the easiest intergalactic destination that will ever exist. Everything described across this episode is the gentle version of the problem. The boundary between what is reachable and what is not is drawn by the balance between gravity and expansion. Inside a bound group, the mutual pull of the members is decisive, and the expansion of space is negligible. Outside it, that relationship inverts, and expansion is the only term that matters. The consequence is that the far future holds a smaller sky than the present one. Over billions of years, the galaxies beyond the local group will redden, dim, and pass out of view entirely, leaving a night sky containing far less to see and far less to reach than the one visible tonight. And there is one more fact about the destination, which sits oddly beside all the rest. In roughly 4 billion years, the two galaxies will meet. The approach that closes 9,000 light-years in 25 million years is the early, slow part of a fall that ends in a merger. The galaxies will pass through one another, and almost nothing will actually collide, because stars are separated by distances so much larger than stars themselves that direct contact is effectively impossible. The gas clouds will collide, new stars will form in the disturbance, and over the following billions of years, the combined system will settle into a single elliptical galaxy with no separate Andromeda in it at all, which produces the quietest conclusion available on this subject. On the longest timescales, the destination is not something anyone has to reach. It is coming. A ship that departs today at 1/10 of light speed and survives every hazard already described would arrive somewhere in a galaxy that is itself already falling toward the place the ship left. The sensible plan, measured strictly by arithmetic, is to stay where we are and wait. That is an answer to the question of how to cross 2.5 million light-years, and it is not the answer anybody sets out looking for. It is simply the one the numbers keep returning. Part 12. The Order. Restated. The order can now be set down plainly, without any of the drama that a list like this usually attracts. On the way to Andromeda, the first thing that kills a traveler is the induced sleep. The second is the machine that has to maintain that sleep. The third is deep time, working on every component aboard. The fourth is radiation. The fifth is the slow degradation of the body itself. The sixth is the interstellar and intergalactic medium. And the seventh, last of all, is the distance. The distance goes last because the distance never touches anyone. 2.5 million light-years is not a hazard in any physical sense. It does not corrode metal, it does not break strands of genetic material, it does not stop a heart. It has no mechanism at all. What the distance does is set the duration, and duration is what converts every other item on the list from a manageable inconvenience into something final. A crossing measured in years would leave almost none of this list standing. A crossing measured in tens of millions of years leaves all of it. The medium sits second to last because it is very nearly harmless in its own right. The space between galaxies is the emptiest environment that exists anywhere, roughly 1 million times thinner than the already thin space between stars. Whole cubic meters of it may contain a single atom. Nothing about that environment is hostile. The difficulty appears only when a vehicle moves through it fast enough that a scattering of individual atoms becomes a steady flux of energetic particles. Even then, the medium is not doing anything. It is simply present, and something is traveling through it very quickly. The body sits above the medium because its failures are real but unusually well behaved. Bone density falls at a predictable rate in weightlessness. Muscle volume declines. Fluid shifts toward the head and press against the back of the eye. The immune system becomes less reliable. Every one of these effects has been measured. Most of them can be partially offset with exercise, drugs, or rotation, and none of them is fast. On any timescale short enough to matter to a human career, the body is survivable. It is only across millions of years that the body stops being a medical problem, and by then, the body is not the issue. Radiation ranks above the body because it is genuinely fatal, and below the machine because it is unhurried. Charged particles and heavy nuclei pass through shielding and through tissue, damaging molecular structures as they go. Living cells repair that damage continuously, and a functioning body can absorb a remarkable amount of it for a remarkably long time. The decisive moment is not when the dose becomes large, it is when repair stops. Radiation does not overwhelm a working biology quickly. It waits for the biology to stop working, and then it accumulates without opposition for as long as the crossing lasts. Deep time ranks above radiation because deep time destroys machines rather than people, and machines are what everything else depends on. Nothing built by anyone has run continuously for 10,000 years, let alone 10 million. Seals harden. Lubricants freeze or evaporate away. Metals slowly rearrange under their own stress. Data storage decays, and the readers for that data decay alongside it. None of this happens dramatically. It happens the way rust happens, patiently and without exception, and the only real defense against it is maintenance, which requires somebody awake to perform it. The machine ranks second because of that last clause. A ship that carries a conscious crew has failures and repairs. A ship that carries an unconscious one has only failures. Thermal control, power generation, radiation shielding, attitude and the cooling systems that keep the sleepers cold all have to hold without intervention, for a duration in which every one of them will certainly need intervention. Each of those systems is survivable alone. Together, unattended, across millions of years, they are not. The machine is dangerous only because there is nobody aboard in a position to notice it going wrong. And the crew is unconscious because the arithmetic left nothing else available. At any speed a vehicle could realistically reach, the crossing outlasts a human life by a factor in the millions. There is no version of this journey in which the people who leave are also the people who are awake for it. Either they are asleep in some engineered sense, or their descendants are awake in their place, which is the same removal distributed over a longer chain of people. Sleep is not one option among several. It is the shape the problem forces every plan into. Which brings the list back around to where it began. The first item is also the one thing the entire plan rests on, and the one thing that has never been done. Every other hazard here has a partial solution, a working prototype, or at minimum, a clear physical description of what a solution would have to look like. The induced sleep has none of those. It is the only step in the sequence that has never once been performed successfully on a human being, and it is the step everything else is built on top of. Stated in its most compressed form, the order runs like this. The sleep, because it does not work. The machine, because nobody is awake to fix it. Deep time, because nothing lasts. Radiation, because repair has stopped. The body, because it degrades. The medium, because the ship is moving through it at speed. The distance, because it is what makes all of the above run long enough to matter. 7 items, and only the first of them has to happen for the rest to become irrelevant. There is a strange comfort somewhere inside all of that, and it deserves to be said clearly. Nothing in the gap between the galaxies is hunting anyone. Not one hazard described across this entire crossing is hostile, or directed, or interested. The medium is not attacking the hull, it is standing still while the hull moves. Radiation is not aiming, it is a background that has been there since long before there was anything to irradiate. Deep time is not patient in the way a predator is patient. It is simply what happens when nothing intervenes. The universe is not resisting the trip. It is only larger than the plan. Every failure in this sequence comes from a mismatch of scale rather than from any opposition, and a mismatch of scale carries no ill will. The gap is quiet, cold, and indifferent, in the plain sense that indifference means the absence of intent. Whatever else this list is, it is not a warning about a dangerous place. It is a description of how much bigger the distances are than the lifespans that would have to cross them. And Andromeda, throughout all of this, has simply been where it is. It is visible tonight from a dark enough sight as a faint oval smudge, wider than the full moon, sitting quietly in the autumn sky. The light entering the eye when someone looks at it left that galaxy about 2.5 million years ago, before the human lineage existed in the form that would eventually look back. Nothing has to be launched for that light to arrive. In the sense that matters most, looking at Andromeda is already a kind of arrival, and it costs nothing but the time it takes to stand still and let the eye adjust. The rest of the arrival is already scheduled. In something like 4 billion years, the two galaxies will meet, pass through one another, and settle over further billions of years into a single larger system. That process needs no crew, no shielding, no cryogenic hardware, and no volunteers. It requires nothing of anyone. The destination that cannot be reached in 25 million years of travel is coming here anyway, on its own schedule, at 110 kilometers per second, and it has never once stopped. Anyone present for that will see it arrive slowly, if the word arrive even applies. The merger will register from this position as a gradual brightening and reshaping of the night sky across hundreds of millions of years, far too gradual for any single observer to notice a change within a lifetime. There is nothing in that prospect to be afraid of, and nothing in the list before it either. The subject throughout has been limits rather than threats: how far a body can be carried, how long a machine can run, and how much time a plan can absorb before the plan quietly stops being about people at all. Andromeda is already on its way here. It has been approaching for longer than there have been eyes to notice, and it will arrive whether or not anyone ever sets out to meet it. Let the distance stay where it is. Let your breathing slow. Sleep well, and good night.